Good afternoon, everyone. Last time we discussed the four subspaces in section 6, and we used one example to discuss those four subspaces, but we haven't finished those. Now let's review the four subspaces and continue on these examples. So the four fundamental subspaces, the row space, which is the column space of A transpose, and the column space of A, the null space of A, the left null space of A. And be careful, some of them are subspace of Rn, some of them are subspace of Rm. And here A is in the m by m format. Now let's look at this example. This is a matrix R in 3 by 5 format. So from this RRE form, it's obvious the rank is 2, right? M equals 3, N equals 5, R equals 2. So here the column space, the rank of the column space is 2, right? Oh, sorry, the dimension, not the rank. The dimension of the column space is 2. And also if you look at by rows, there are also 2 pivotal rows. So the dimension for the row space are also 2. So the dimension of the row space is the rank. The dimension of the column space is also the rank. And those 2 pivotal rows or those pivotal columns, they are the basis. They are the basis for the row space and column space respectively. So number 2 is the column space. Right? The dimension of the column space is the rank R, which is 2. The pivot columns, the first and fourth columns are bases. Now, the null space. So from the matrix R, we know first and fourth columns are pivot columns. So x2, x3, and x5 are free variables. So those we can extract the matrix F from this matrix R and fill up the null space matrices as S2, S3, S5. Those are spatial solutions, and also those are 3 columns in the matrix M for the linear system Rx equals 0. And of course, those 3 spatial solutions are independent. So that implies the dimension of the null space is m minus r, which is 5 minus 2 equals 3. And those three spatial solutions form a basis for the null space in R. And we can express the solutions in the null space as a linear combination of those 3 spatial solutions, right? So that is the third one, the null space. Now let's look at the last one, the left null space. How can we define the left null space? That will be all the solutions to the linear system R transpose Y. We use Y equals to the 0 vector. We use Y to denote the solutions in the left null space. And it's the same as you use A transpose Y, right? Now let me explain the R transpose Y. So R transpose will be 1, 3, 5, 0, 7, 0, 0, 0, 1, 2. The last row is 0. The last column is 0 in the transpose. So times Y. Y is the vector from R3, right? Y has 3 components. So that equals the vector 0, right? So if we write in this way, that will be each row times the 3 component, right? Y1, Y2, Y3. So that is the same to write it as the linear combination of each columns. So here that is the first column plus Y2 times the second column plus Y3 times the third column. It doesn't matter, you write it as a row, okay? You write it as a row. So it's a that is R transpose, yeah, times Y. So if you express in the row, that will be this way, okay? That will be this way. And also we can understand the R transpose Y equals the 0 vector. You can put the transpose on both sides according to the formula, right? R transpose transpose, that is R, and then will be Y transpose times R. AB transpose, that will be B transpose times A transpose, right? So Y transpose R equals 0 transpose, right? So if it's 0 column vector, that becomes 0 row vector. So that from here you will see it's the linear combination of those 3 rows in matrix R gives the 0 rows. So Y1, Y2 needs to be 0, right? And the last row, Y3 can be any real numbers. That's why we said Y3 is free. So the solution will be 0, 0, Y3, where Y3 is all the real numbers. But the first two components should be 0. Y1, Y2 should be both 0, right? So this is the multiple of the basis vector 0, 0, 1. This is the all the solutions. This vector Y represents all the solutions in the left null space 0, 0, Y3. Then how can we write its base? Standard base, that will be 0, 0, 1, right? 0, 0, 1. Any other solution can be expressed as a multiple of this basis vector. And there is only one free variable. So what is the dimension of the left null space? What is the dimension of the left null space? Which we write A transpose or R transpose. It's the same thing. So the dimension should be 1, right? The dimension should be 1. Because it's only one free variable. It's a multiple of those, and it's only one basis vector. How can we get this one? That is M minus R. M is 3. The rank R is 2. And this one is the subspace. The left null space is the subspace of R3. The solutions in the left null space, the vector Y has 3 components. The vector Y is coming from the R3, right? So the left null space is the subspace of R3. The dimension is 1, and its standard basis vector is 0, 0, 1. So that is the 4th subspaces. Now let's check example 1. Example 1, this matrix A has 1 row and 3 columns. So M equals 1, N equals 3, and the rank R equals 1. How can we understand the rank R equals 1? So if you look at by columns, if you look at the column space for the matrix A, then there are 3 columns, but each column is from the dimension R, right? From the real number R. Each vector has 1 component, right? The first column is the pivot column 1, and the second and third column are the multiples of the first column. So that is how we understand the rank is 1. And especially each column vector has only 1 component. So the column vector are the vectors from R, which means they are real numbers. They are from R1, right? From R1. The dimension is 1. And in another way, how can we understand the rank equals 1? The rank R should be less than the M and should be less than N. R is the rank, which denotes the true size of the matrix. So the rank should be less than or equal to the number of rows M, and also should be less than the number of columns. So should be less than the smaller one of those 2 values. So R is less than or equal to 1, and it's 1, right? It's 1. The rank is 1, and there is 1 rows. And by the way, we haven't discussed the rank 0, right? We haven't discussed the rank R equals 0. And this is not a 0 matrix. This A is not 0 matrix. Of course, the rank cannot be 0. Now, let's check those one by one, okay? Let's check the row space, column space, and the null space and the left null space one by one. So the column space, we have already mentioned the dimension of the column space is 1, right? Is 1. And it's a subspace. It's a subspace of R, right? It's a subspace of R. The dimension is 1, and the vector is the basis vector is 1. There is only one basis vector. The basis vector is 1. It's just a number, right? Just a number. So any vectors in R, can be expressed by this basis vector. That means the column space gives all the real numbers. The column space is all real numbers, which is R, the dimension, which means the dimension is 1, right? R1. If it's R2, that will be XY plane, right? We understand R2 and R3, but R1 just means the real number 9. Real number 9. And any real number can be expressed by the basis vector 1, right? Can be expressed by the basis vector 1. So that is number 1. Number 2, the row space. Row space, of course, the dimension of the row space, which is the column space of A transpose, that is also equals the rank, right? And the rank equals 1. The basis vector is this row, right? the basis vector. The dimension is 1, which means there is only one basis vector. So this row space is a subspace of R1 or R3. The row space is a subspace of R1 or R3. Think about the vectors in the row space. How many components? How many components does the basis vector have? So it's the vector with 3 components, right? Actually, that is the 9, okay? Is the 9 in R3. A 9 in R3. Which 9? The 9 is passing through this vector 1, 2, 3. It's a multiple of this basis vector that gives the row space. Of course, it's a subspace of R3. That means it's a straight line in 3-dimensional space. Okay. Now number 3, the null space. The null space, which means we need to solve ax equals 0. Ax, so that will be x1 plus 2x2 plus 3x3 equals 0. And we know that only one pivot column, right? Only one pivot column. So you can set up the x2 and the x3 as free variable, right? Free variable. So, and of course, from here you can check this is the plane in R3. Actually, it's a plane in R3. The equation x1 plus 2x2 plus 3x3, that is the plane in R3. And of course, the dimension of the null space, that will be 2, right? That will be 2. How can we get 2? M minus R, that is 2. And we know that if the rank is R, then there will be M minus R free variable, and there will be M minus R spatial solutions. So of course, the dimension, there are 2 spatial solutions in the null space. Of course, the dimension will be 2, and it's a plane in R3. Number 4, let's check the left null space. Which is the A transpose Y equals 0 vector. So that will be 1, 2, 3 times the Y, okay, times the Y. Y1, there is only one component, equals the 0 vector. What is Y1? So the Y, the solution actually will be this 0 vector. This 0 vector, the dimension is called 0, right? This is the 0 space. So the only solution to A transpose Y is Y equals 0. We have already explained introduced the 0 space, right? This is called the 0 space Z, capital Z, with the dimension 0. This is the spatial we called the dimension is 0. The dimension of the left null space is 0. How can we get it 0? That equals M minus R. M and R are both 1. So this is the spatial case, okay? And this 0 space is the subspace of Rm, of R1. Are you clear? I think the first three, column space, row space, null space, it's easy to get, right? To figure out the dimension and to figure out how it looks like for those three subspaces. Be careful of the number 4, the left null space. Left null space, that is A transpose Y equals 0 vector, and we figure out the solution is the 0 vector. So that is has only one 0 vector, that is called the 0 space with the dimension 0. So those are the conclusions. From these examples, we can get those conclusions from the previous slide. Column space, the dimension equals the rank R, right? The row space, the dimension equals the rank R also. The null space, the dimension equals n minus R, 2. Left null space, the dimension equals n minus R, which is 0. So that is the first example. Now let's look at second one. Okay, second one. We will also look at those 4 subspaces. So this is the matrix 2 by 3, 2 rows, 3 columns, and the rank is 1. It's easy to tell, right? Second row is 2 multiplied by the first row, so there is only 1 pivot row. Or first column is the pivot column because second and third column are the multiples of the first column. So the rank, there is only 1 pivot row as well as 1 pivot column. So the rank is R equals 1, right? Rank R equals 1. So the row space is the same 9 through 1, 2, 3, right? Of course, the dimension of the row space is the rank 1, right? Equals 1. That is the 9, right? That is the 9 in R3, right? Because it's a subspace. It's a subspace in R3. And the null space must be the same plane, x1 plus 2, x2 plus 3, x3 equals 0. You can check that the null space, this is the row space. Number 2, the null space, ax equals 0. X1, x2, x3 equals the 0 vector. So actually you are going to get 2 equations, but the second one is the multiple of the first one, right? 2x1 plus 4x2 plus 6x3 equals 0. That is the multiple of the first plane, right? So that the null space will be the plane in R3. The null space is a plane in R3, so the null space dimension will be 2, will be n minus r, right? Will be n minus r, which is 2. That is the row space and the null space. Now let's check the column space. Column space, all the columns are multiples of the first column, 1, 2. So the column space dimension is also 1, right? Equals to the rank. That is 1. Because the other 2 columns are the multiple of the first one. And if we check the left null space, that has the solution 2 minus 1. Let's check that. The number 4, A transpose Y 1, 2, 3, 2, 4, 6. Try to take note, okay? Try to take note. And those examples actually are pretty easy to explain those 4 subspaces. y1, y2 equals 0. So you will notice that we will get y1 plus 2y2 equals 0. And the second and the third equation will be 2y1 plus 4y2 equals 0. 3y1 plus 6y2 equals 0. So it's the same as this one, right? So we can write one solution. We can write one solution 2 minus 1, right? 2 minus 1. Actually, from the from here, you will notice that if we set up one value for y2 is minus 1, the other one is decided. So actually, the dimension of the null space is m minus r. The dimension of the left null space, that will be m minus r. 2 minus 1 is 1. Because to solve those, that means two variables need to satisfy one equation. There is only one free variable. If you freely choose one variable, then the other one can be fixed, right? Can be fixed. Or you can still get the RE form. RE form, there is only one pivot column, right? The first column is the pivot column. Second column is the free column. So there is one spatial solution, right? y2 is the free spatial solution. It's the same, okay? So the dimension is 1, which is m minus r. Now let's finish here and then we summarize for example 1, 2. So you will notice that the dimension of the third one, dimension of column space and the dimension of the left null space, the sum of those are m, which is 2, right? Which is 2. The column space, basis vector, left null space, basis vector, they are perpendicular line. We will discuss this perpendicular property in the next chapter. Okay, we will start chapter 4 in 20 minutes. Okay, so let me summarize for those 2 examples a little bit. Let me save the file right now. So let's summarize it. Okay. So if A is in m by n format and the rank is R, there are some special relations between those 3 numbers m and R. So first, the dimension of the row space, which is A transpose column space, the dimension is R. And the dimension of the null space that is n minus r, right? Because r, the rank is r, there will be n minus r spatial solutions. So that the dimension is n minus r. So from here, actually, the dimension of the row space plus the dimension of the null space, the sum of those two dimensions, that is n, that equals the number of columns. And then let's check the dimension of the column space of A, that is R, that is the rank also. And the dimension of the left null space, that is M minus R. So the sum of those two dimensions will be M. What is M? M is the number of rows in the matrix A. And this is the important relation, okay? And we know those four are subspaces, right? Those four are subspaces. Are you clear? The first, the row space and the null space, they are subspaces of Rn, right? The columns, the row space and the null space, they are subspace of Rn. And the sum of their dimensions gives n. Number two, the sum of dimensions of column space and the left null space, that is n. And they are subspaces of Rm. So are you clear about those relationship for those four subspaces? In chapter 4, we will discuss the orthogonality between those four subspaces. So have you finished the note? And actually, this is the fundamental theory of linear algebra part 1. Fundamental theory of linear algebra part 1. The column space and the row space both have dimension r, which is the rank, okay, which is the rank. The null spaces, which including the null space and the left null space. This is the null space dimension. M minus r is the left null space. And we will give fundamental theory of linear algebra part 2 in the next chapter, okay, in the next chapter. So that is the relation, and we use some examples. The reason we give those fundamental theory at the end of chapter 3 because we need a lot of knowledge to understand. Even though those are three simple number m and r, but if you couldn't understand those four subspaces, the solution to the null space and the rank, then you couldn't understand those relationship. Okay. Now let's review the key ideas for this section. The R pivot rows of R of the matrix RRE form matrix R are basis for the row space of R and A. They are equivalent, right? For the RE form matrix R and the original matrix A, they are the same. So is the same for columns. The R pivot columns of A are a basis for its column space. And there will be n minus r spatial solutions. These form a basis for the null space of A and R. Here they write A and R. That means they are equivalent, right? To solve AX equals 0, that is the same as to solve RX equals 0. And those two number 4 and number 5, we didn't discuss the left null space in details, so we can skip number 4 and number 5. But you need to know what is the dimension for the left null space, and is it a subspace of Rn or Rm? Trying to figure out the FTC of linear algebra about left null space. That will be enough. Okay. So it's almost time. Okay, almost time. Let's take a short break. Then we will start chapter 4. In chapter 4, we will discuss the orthogonality for the 4 subspaces. So we will focus on the topic orthogonality. There will be 4 sections in this chapter. I think I am planning to cover 3 sections of those. Okay, 3 sections in chapter 4, and I think we are almost done this about this course. So let's think about the orthogonal vectors. We have already studied this definition. How can we tell 2 vectors are orthogonal vectors? The dot product of those 2 vectors gives 0, right? Then those 2 vectors are called orthogonal vectors. Now we will expanded this concept orthogonality to the spaces, okay, to the spaces. 2 vectors are orthogonal when their dot product is 0. So we can express the dot product in this normal way or in this way. That is the inner product, right? We also call the dot product as the inner product. So this chapter moves to orthogonal subspaces and orthogonal bases and orthogonal matrices. We will focus on the orthogonal subspaces and bases. If we have more time, we will discuss orthogonal matrices. So that the orthogonal subspaces, that means there are 2 subspaces. The vectors from those 2 subspaces, or the vectors in those 2 bases, or the column vectors in those 2 matrices, they are orthogonal pairs. So it's like the triangle, okay, triangle. The right triangle, we have this vector v and w, and this hypotenuse is v plus w. So we can take the norm of v is a, the norm of w, the vector w, is b, so that equals the norm of v plus w, the length of the hypotenuse, which is the norm of v plus w, right? So the 2 vectors v and w are orthogonal to each other. We can use the inner product to express it, right? So if any vectors in this direction v and any vector in this direction w, they are orthogonal pairs. Are you clear? They are orthogonal pairs. So orthogonal vector, the inner product gives 0, and that also gives a right triangle. Then we have this inequality, right? We have this equality. Now let's read the definition of orthogonal subspaces first. Then we check what is the orthogonality between those 4 subspaces. 2 subspaces V and W of a vector space are orthogonal if every vector V in the subspace big V is perpendicular to every vector W in the subspace W. So are you clear about this definition? Every vector from this V is orthogonal to every vector W in this V. So inner product V and W equals 0 for be careful, this 0 is a number, right? This 0 is not a vector, this 0 is a number. The inner product gives the 0 for every V and W from those two subspaces respectively. Are you clear? Are you clear about the definition of orthogonal subspaces? Now we are going to check those two statements. The row space is perpendicular to the null space. The column space is perpendicular to the left null space. Those two are important conclusions we will focus on in this section. So orthogonal subspaces, which means the subspace V is perpendicular to W. They are the same thing, right? They are the different term, but it's the same meaning. Perpendicular to each other, or they are orthogonal to each other. They are orthogonal subspaces. Now let's check the some examples then. Let's read some examples in the three-dimensional space in our daily life. Then we will explain those two statements. So the floor, okay, try to think about this example. If you stay at your dormitory or at your bedroom, okay, check that. Example 1. The floor of your room is the subspace V. So the floor is a plane, right? The line where two walls meet is the subspace W. So it's a line, okay? It's a line. Those subspaces are orthogonal. So are you clear? Let me open the video, okay? Let me open the video. But I can't see my own pictures. Yeah, let me just open my own pictures. So this is like a floor, okay? This one is like the floor, but it's a plane, right? It's a plane, you can extend it infinity. And then at the corner, there are two walls, right? There are two walls. Those green cover, those are two walls. So you will notice there is a vertical line, right? There is a vertical line. This green one, that will be the line where two walls are meet to each other, right? So what we said in example 1 is this line where two walls meet, that will perpendicular to the floor. Are you clear? This line, two walls are meet. This is the line. So you will notice that this is the vertical line up to the floor, and the angle will be 90 degrees, right? The angle will be 90 degrees. And be careful, okay? Be careful. This plane, this is the example in our daily life. This plane, it's a plane in three-dimensional space, because we are living in a 3D space, right? This is a plane in 3D space, and this line where those two walls are meet, this is also a line in three-dimensional space, and this line is up to this floor. So we will see this line is perpendicular to the floor. This is a very easy example, okay? This is a very easy example. So did you get it? Did you get it? That is the example 1. So we said this line is perpendicular to the floor, and the floor is the plane, right? Is the plane. There, the V and W, the floor is a plane in R3. So it's a subspace in R3. And that vertical line is also a line, but it's a subspace in R3. So those two subspaces are perpendicular to each other, or those two are orthogonal. Those two subspaces are orthogonal. And you can check that every vector inside the flow, every vector inside the flow in this plane will be perpendicular to the vector up the meeting line, up this vertical line, right? Are you clear? Every line that lies in the flow, which means every vector from this subspace V that is perpendicular to the meeting line of two walls, this green one I showed you. Are you clear? So it's first example, okay? It's very easy to get. That is what I said, okay? This figure is what I said. The V is the orthogonal. The V is a plane. It's a plane like the floor. And this W is the perpendicular line, which up to the floor. This W is a 9. So they are both subspaces, right? So V, you can take this V as the floor. You can take this W as the 9 where two walls meet. Both V and W are subspace in R3. Both V and W are subspaces in R3, and we know the plane is the plane, the subspace W is the plane, so the dimension is 2, and this 9, the dimension is 1, right? Now let's check example 2. Two walls look perpendicular, but they are not orthogonal subspaces. So like the example I did, okay? Two walls, they will meet at one line, and you feel like the angle between those two walls will be 90 degrees, right? Like here, there are two walls, V and W. Then the angle between those two planes will be 90 degrees, but they are not called perpendicular. Okay, they are not the orthogonal subspaces. Why? Those two walls meet at this line, right? This vector. So this line, the vector on this line is spatial. That is the intersection actually, right? It's the intersection of those two planes. So this line is in the plane V, and it's also in the plane W. That means this line, the vector on this line should be perpendicular to itself. If a line is perpendicular to itself, the inner product equals 0. When W equals V, when they are the same vector, that means V is 0 vector. But V is not a 0 vector. V can be any vector on this line, right? V can be any vector on this line. So that's why those two planes, those two subspaces are not orthogonal. Think about the definition of orthogonal subspaces. Every vector in V should be perpendicular to every vector in W, right? But there is a vector that that in both V and W, and this line of course cannot be perpendicular to itself. If it's perpendicular to itself, then this vector should be the zero vector, but this is not a zero vector, right? This is not a zero vector. So this gives an example, non-orthogonal planes. And you can think about it. Two walls, the dimension of these two planes are both 2, right? The dimension of one wall, one side wall, and the dimension of another side wall are 2. So the sum of those two subspace will be 4. That is greater than 3, which is the dimension of whole space R3. We are talking about the examples of walls in our room, right? We're living in a 3-dimensional space. So it's impossible, right? The orthogonality is impossible if the sum of dimension 2 subspaces is greater than the dimension of the whole space R3. Now, let's check those, after review those 2 examples related to our life, then let's check the statement, okay? The statement. The null space and the row space are orthogonal subspaces of Rn. And from fundamental theory of linear algebra part 1, we know they are subspaces, right? They are subspaces of Rn, and the dimension of this one is n minus r. The dimension of this one is r. Now, let's check the null space. So for the null space, that will be Ax equals 0, right? Ax equals 0. So we can express the matrix A using write the m rows, okay? M rows. M row dot x, right? Dot the vector x. X is the column vector. So that means each dot product, row 1 dot x, row 2 dot x until row m dot x is 0. That means each row is perpendicular to x, right? Each row is perpendicular to x, to the vector x. Of course, those x is the solution in the null space, right? Each row is perpendicular to the vector x. And where is the x? X will be every vector in the null space. Here, each row in matrix A, that means we included the pivotal rows, right? If the rank is R, that will including the R pivotal rows. So which means any vectors in the row space, that will be, when they dot with the X, that will give 0. So the first equation says that row 1 is perpendicular to x. The last equation gives row m is perpendicular to x, which means every row has a 0 dot product with x. Then x is also perpendicular to every combination of the rows. So did you get it? Every row, the row vector, any row vector can be expressed as any row vector from the row space. How can we denote the row space? column space of A transpose, right? Any row vector can be expressed as the linear combination of, so C1 times row 1 plus C2 times row 2 plus Cm times row m. Since each row has a zero dot product with x, then the linear combination will also have the zero dot product with x. So that means every row vector will have zero dot product with x. What is this x? This x is the solution to the linear system Ax equals 0, which means this x is every vector from the null space. That's why we said the whole space, the whole row space is orthogonal to the null space. And we know they are both subspaces of Rn. The dimension of null space is n minus r. The dimension of row space is r. So the sum of those two dimensions gives n, which is the whole space M. And those two are orthogonal subspaces, right? Row space and null space, they are orthogonal spaces. Now let's check example 3. Trying to understand the null space is perpendicular to the row space. Let's check the rows. 1, 3, 4, 5, 2, 7. Let's find the rank of this matrix trying to get the RRE form. 5, 2, 7. First row is the pivot row. So that will be row 2 minus 5 times row 1. Row 2 minus 5 times row 1, so we get 0. 2 minus 15 minus 13, 7 minus 20 minus 13. And then you can multiply by minus 1/13 for the second row, you get 0, 1, 1. But this is not the RRE form, so we will choose the second row as the pivot row. Then row 1 minus row 2. Row 1 minus row 2. It's row 1 minus 3 times row 2. So it's 1, 0, 4 minus 3, we get 1. Now this is the RRE form of matrix A, which we can also use the matrix R, right? We can also use the matrix R to denote that. Now what is the rank? What is the rank? So the rank is 2, right? The rank is 2. Then the dimension of the row space, the dimension of the row space will equals the rank 2. What is the dimension of the null space? That will be m minus r. What is m? This is 2 by 3. M equals 2. 2 rows, 3 columns. So the dimension to the null space will be m minus r. Is it a problem? Oh, sorry, will be m minus r. Will be m minus r. That is 1. Right? That is 1. The null space dimension will be 1. What is the spatial solution? We can find this is one spatial solution. We can give one spatial solution. The x3 is the free variable, right? X3 is the free variable. So actually you can get another spatial solution. According to our method, we can get the spatial solution is 1. X3 is 1. X2, X1, and X2 are minus 1. It's okay. You get 1, 1, minus 1. It's a multiple of the spatial solution, but the dimension is 1, right? So from basically we figure out those, okay? We figure out those, and we know according to linear algebra FTC part 1, the sum of those equals m, right? Equals n, dimension of those. Sorry, it's a little noise from outside. They play some music. Let's continue, okay? So the dimension equals m. Now the rows of A, which is 1, 3, 4, 5, 2, 7, those two vectors are perpendicular to the solution in the null space because it gives the zero dot product, right? It gives the zero dot product. And actually we know that every row vector, every row in matrix A or in matrix R, it doesn't matter, right? It doesn't matter. In R, it's the same. In matrix R, there are two rows, right? Two rows, 1, 0, 1, 0, 1, 1, that multiple by x. So Rx, we get 1, 0, 1, 0, 1, 1 times the x, 1, 1 minus 1. 1, 1 minus 1 is also the solution in the null space, but usually we express the spatial solution in this way because we set up the free variable x3 equals 1. It doesn't matter, right? 1, 1 minus 1 is the multiple, is the scalar of the spatial solution. So here we get 0, 0. First row times this solution, 1 plus 0 minus 1 equals 0. Second row multiple by x, we get 0 plus 1 minus 1 equals 0, right? So it's the same for matrix R as well as in A. So what does this mean? That means the row space we write in the column space of A transpose is orthogonal to, or we call the orthogonal subspaces. Row space and the null space, they are orthogonal subspaces. And by the way, they are subspaces of R2 or R3. They are both subspaces of R2 or R3. And the dimension of those equals m. So orthogonal subspaces, they are subspaces of R3 actually. So that is example 3. Have you finished the note? Yeah, give you one more minute to finish the note. Have you finished the note? All right. Now let's check another one. Okay, another one. The left null space and the column space are orthogonal subspaces. So those two, the column space and the left null space, they are orthogonal subspaces. So first, we know that the dimension of the column space is the rank R from fundamental theory of linear algebra part 1. And the dimension of the left null space is m minus r, right? M minus r, and their subspace of Rm, right? They are subspaces of Rm. Now let's check the left null space. Okay, let's check the left null space. So we can express the A transpose Y in this way. I can write the A transpose as by columns, column 1, column 2 until column n, then transpose times the vector y, right? Times the vector y. So those are n columns. So in its transpose, that becomes n rows. Are you clear? So actually here, the column 1 transpose, that becomes the row 1. That becomes the row 1 in the A transpose. That's why we write in this way. That's why we express by rows. Column 1 transpose, the vertical columns becomes the horizontal rows in A transpose. So that will be n rows, right? Those n columns transpose, that becomes n columns. Then that multiple by the vector y gives the dot product 0, right? So that will be the column I transpose y gives the 0, dot product 0. So each column is perpendicular to the y, right? So from here, column I transpose dot y gives 0. That means each column is perpendicular to y, to the vector y. What is y? Y is the solution, right? Y is the solution in the left null spaces. In the left null spaces, we use this notation. And again, each row, each column is perpendicular to the vector y. Combination can be any combination of each columns that is also perpendicular to the vector y, which means every column vector from the column space that is perpendicular to the y from the left null space. Are you clear? every column vector from the column space is perpendicular to the y from the left null space. That's why we said they are orthogonal subspaces. And here you will notice again the sum of those two dimensions gives m, right? The sum of dimensions gives m. Gives m. And they are orthogonal subspaces. They are subspaces of Rm. So there are two important conclusions. Okay, there are two important conclusions. Now let's check the orthogonal complement. Then we will check FTC of fundamental theory, FTC of linear algebra part 2. The fundamental subspaces are more than just orthogonal in pairs. Their dimensions are also right. Two lines could be perpendicular in R3, but those lines couldn't be the row space and the null space of a 3x3 matrix. The lines have dimensions 1 and 1, R into 2. The correct dimension R and n minus R must add to n equals 3, right? So let's check the orthogonal complement. The orthogonal complement of a subspace V contains every vector that is perpendicular to V. So we use this notation V perp to denote its orthogonal complement. Here we said two lines could be perpendicular, but they are not orthogonal complement to each other. Are you clear? In R3, like you can put two vertical lines, right? But their dimension are both 1. The sum of their dimension is less than 3. So they are not orthogonal complement to each other. But the null space and the row space, they are orthogonal complement to each other because the sum of their dimension gives n. Are you clear? The dimension of the null space and the dimension of the row space, the sum gives n. They are subspaces for Rn. The sum of their dimensions gives m. So they are orthogonal complement to each other. So we can express in this way the row space is orthogonal to the null space. So the ver perp, you can take this one as the subspace V, the V perp, which means the orthogonal complement. Be careful of this notation. It's a orthogonal notation. That equals the null space. Or in another way, we can see the null space perp. Null space perp also equals the row space. We are not going to use the name, okay? When you use those notation, you should be able to check you should be able to read what does those four subspaces mean. Now, after this concept, let's check the FTC of linear algebra part 2. Null space is the orthogonal complement of the row space in Rn, which implies the sum of their dimensions, the sum of those two subspace dimensions gives n, and one is R, the other one is n minus R. And they are orthogonal to each other, and they are orthogonal complement to each other. Then the next one, the left null space and the column space, they are orthogonal subspaces. They are both subspaces in Rm. And the dimension, the sum of their dimensions gives M. So they are orthogonal complement to each other. Are you clear? So even though we only give this one statement, but that gives a lot of information combined with FTC part 1. Are you clear? They are orthogonal subspaces, and also they are orthogonal complement. That's why we will focus on those 4 subspaces in section 6. And as I said, if you couldn't understand chapter 3, then it would be very struggling to understand in chapter 4. It's based on chapter 3, based on those 4 subspaces. And what does those subspaces mean? Column space, row space, null space, left null space, and how to figure out the rank, how to figure out the dimensions of each subspaces. That is come from chapter 3. If you could understand chapter 3 very well, then it's easy to move forward on chapter 4. So please try to review all those notes, okay? We will stop here today, and we will meet on Wednesday.